Alright, so in this second part of Chapter 7 video, we are going to look at electrons. More specifically, what electrons do, how electrons behave, if there's anything that we can do with these electrons. We'll be learning about that as well. So, electrons, as we said, have particle and wave functions. We're familiar with the particle function, but now we're going to start looking at the wave function a little bit. And so we can use some light principles for electrons. And this is known as the de Broglie relationship. Right? And what de Broglie found was that the wavelength of an electron, and what we'll see is we can apply this to really anything, is equal to h. So we saw h in the previous video for Planck's constant, divided by m, which is the mass of what we're looking at, times the velocity. So h is equal to Planck's constant, 6.626 times 10 to the negative 34th. Now again, you will be giving these constants and everything on an exam or on a quiz, times m, which is actually the mass of whatever we're looking at. Usually it's the mass of an electron. Now, here's where it gets a little tricky. So we said the units for Planck's constant is joules per times second. So second's pretty self-explanatory, but joules. If you look at mass and velocity, there's nothing that'll cancel out with joules. But if you remember what joules are kilograms times mass squared divided by second squared. Times meter squared, divided by second squared. And so the mass, whatever mass that we're talking about here, has to be in kilograms. So if we're going to look at for the mass of an electron, it has to be in kilograms. I will give you the mass of an electron in kilograms. It's 9.11 times 10 to the negative 31st kilograms. This mass has to be in kilograms, no matter what we do. And then times velocity. Velocity has to be in meters per second, because the seconds and the meters will cancel out, and then you'll be left with meters because we're calculating a wavelength. So, how in the world can we do this? So, how we can do this, let's look at a problem. Number 53. We're going to look at a baseball. And we want to know the wavelength of the baseball. This baseball weighs 143 grams. And it travels at about 95 miles per hour. So a major league pitcher throws this baseball. We want to know the wavelength of this baseball. So, the first thing we need to do, like what we saw before, is we're going to use wavelength is equal to Planck's constant divided by mass times times velocity. We know that the mass has to be in kilograms, so let's convert 143 grams into kilograms. 0.143 kilograms, right? Because going from grams to kilograms, you divide by 1,000. Going from kilograms to grams, you multiply by 1,000. Because you're going from something bigger, or something smaller to something bigger, so you're going to divide by 1,000. Now, converting miles per hour to meters per second, if you ever had to do that, I would give you the conversion factor, which is you divide by 2.237. So if you divide 95 by 2.237, you get 42.47 meters per second. And so now we've converted everything. We're ready to put it into our equation and then solve for the wavelength that this baseball is traveling. So kilograms, and then this velocity. So when we do that, then we just solve. So when we finally solve it, we get our wavelength is equal to 1.09 times 10 to the negative 34th meters. That is really long. We can also do, so let's turn it into nanometers. So we can multiply it by 10 to the 9th. And so it'll be 1.09 times 10 to the negative 25th nanometers. So obviously basketball or baseballs aren't pitched at a speed with which they can actually get any sort of wavelength, and obviously this is an exaggeration of what this de Broglie's relationship, but it just shows that we can use mass and velocity to calculate a wavelength. And so for you to practice this, I want you guys to do question numbers 51 and 54, and this will also be due on Friday. So I know it's a lot of stuff for Chapter 7 due on Friday, but we really need to kind of push a little bit to get through, to review Chapter 7 so that we can get through Chapter 8 and through Chapter 9 for you guys' next exam. But do it in a way that you guys are actually learning the material so that you guys can know it and be successful in the exam. So, electrons also have particles and wave functions. However, trying to reconcile the two natures of a wave particle, or the wave and the particle, is very difficult. Also about electrons, there's two parts of an electron that we really want to know. We want to know the position of the electron around the nucleus, but we also want to know the speed and how fast it's traveling. So the problem, though, with these two things is that the more we know about the position, the less we know about the speed. And the more we know about the speed, the less we know about the position. And so the way that mathematicians and scientists have gotten this around is the uncertainty principle. And how, we just don't understand what these things are. And so they've come up with the equation. I'm just showing you this equation just to show you that what the scientists have come up with. So we get delta x times mass delta V is greater than or equal to a constant h over 4 pi. And so this delta x is uncertainty in the position. The speed, or the velocity, is this unit. And so the more we know about the position, the less we know about the speed, and the less we know about the speed, the more we know about the position. And so what ended up happening was there was a person, a scientist, named Schrödinger. And if you've taken a psychology class or any other type of class, you guys are familiar with Schrödinger's cat, where is he alive or is he dead? It depends on where you look and all this other stuff. We're not really going to talk about it, but Schrödinger came up with an equation. And here's his equation. H psi equals E psi. So H is just, it's known as an operator. It's not important because we're not going to derive it. We're not going to tell you how you use it. I'm just showing it to you. So this is just, it's a ton of mathematical equations showing the total energy within a system. So that's H is equal to E, which is the energy of an electron. Those psi's are what's known as wave functions. Again, different mathematical formulas that we're not going to really get into. But what's important is when you solve this, when you solve this equation, or when you put it in a computer and it solves you get 4 different numbers back. And those are the things that we're going to focus on, and those are known as quantum numbers. And so there's 4 different quantum numbers. There's n, which is the principal quantum number. And this one is very important to tell us the energy and the size of the orbitals. And then what you have is we get another quantum number, which is L. This is the angular momentum quantum number. And this tells us the shape. We're only going to deal with 4 L numbers. 0, 1, 2, 3. So whereas 0 denotes an S, 1 denotes a p orbital, 2 denotes a d orbital, and 3 denotes an f orbital. Those are the only ones we're going to focus on, but again, those are L's, or the angular momentum quantum number. You have another number, ML, which is the magnetic quantum number, and this denotes the orientation of the orbital. And that's orientation in 3-dimensional space. And so at the end of this, I'll tell you guys to be familiar with how they actually look, because there's a reason why you have ML. So S only has 1 ML, and that's 0. P has 3 MLs, and that's a -1, a 0, and a 1, depending on its orientation. And then as you add orbitals, as you go up to D and to F, you also add orientation numbers. And then you have one more, because as we've talked about in Chapter 8, so the end of Chapter 7, the beginning of Chapter 8 kind of melds into one unit, is the spin quantum number. And the spin quantum number denotes whether an electron is +1/2 or -1/2. Right? It's the spin of those electrons, and we said if you have 2 electrons next to each other, they can't have these 4 numbers exactly the same, and so if N, L, and ML are the same, then MS has to be different. So, how in the world... So N's are pretty self-explanatory. You cannot have an N of 0. And the reason why is because there's an equation to calculate the energy of an orbital or of a sublevel using N. And so we can calculate energies of these different levels using this equation. You should just be familiar with the equation. You used it in lab. It will not probably be on the exam, but you should still be familiar with it. There might be some Pearson homework using it, where the energy of N, or of the level, sublevel, is equal to -2.18 times 10 to the -18th joules. So this is Rydberg's constant. Rydberg came up with the hydrogen and how hydrogen electrons move. And we're going to multiply that. And unfortunately I ran out of room, so I'm going to have to write up below it. We're going to have to multiply it by 1 over n squared. So it's -2.18 times 10 to the -18th joules times 1 over n squared. So if an n is 0, you can't do that because 1 divided by 0 is not real. And so your first n level has to be 1, and then you go up to 2, to 3, to 4, and so on and so forth. And so quantum numbers are very important. Quantum numbers describe where electrons are. So, another important thing to note has to do with these L's. And so, how do we know which sublevel has which orbitals in it? So, when we look at these different ways that orbitals are drawn, we usually draw 1s, and then we usually have 2s, 2p, 3s, 3p, 3d, and then 4s, 4p, 4d, 4f, and so on and so forth. So how do we know 1 only has an s, 2 has an s and a p, 3 has an spd? The way you do that is the number of L's is equal to n minus 1. And so for 1, so for n equals 1, that would be then 0. And we said L of 0 is S. If n equals 2, actually let's circle it so we can see it. So if n equals 2, which is right here, so 2 minus 1 is 1, but you can also have a 0. You also have a 0. You can't have an L that equals the n. It's impossible. There's just not enough energy available. But you can also have one that's the next step down. So 1 is P, so there's 2P, but you can also have the next step down, which is S. And so then for 3, you can have a 2, which is a D, but you can also have the 1, which is the P, and the 0, which is the S. And so don't just think that because it's n minus 1, you only have the 1. You also have the ones that are preceding it, that are lower than it. So the other thing that we need to do with these orbitals and how things look is we need to be familiar with pages 325 through 327, and that's the shape of the orbitals. We should be familiar with how these orbitals look, and the reason why we draw electrons as circular is due to the shapes of all the orbitals combined. And so I hope this helps just recap what you guys should have learned in Chapter 7 and maybe explained a couple things maybe in a little bit more detail. If you guys have any questions, please, oh please, come see me now about it so that we can go over a lot of the different things before the exam.